First of all, I'd like to thank Lars for that very kind introduction. And as he mentioned, what I'd like to do is tell you something about the field of spintronics, which is essentially a new research field about 20 years old. And it concerns how we could basically create new materials and new devices that could be useful. And there's both a lot of very interesting fundamental physics that's being discussed at the workshop here at the KITP over the past few weeks and the next few weeks. But also, it turns out to be a very interesting field of research, which is not only breaking ground from a fundamental perspective, but it clearly has technological applications. And what I want to do is show you, I'm really going to concentrate on my own work, which covers the last 20 years. And I want to show you basically how we've taken some very interesting materials, new materials, which we essentially build one atomic layer at a time, combining magnetic and non-magnetic materials, and we could use these to control the flow of currents of spin-polarized electrons to enable new phenomena and then eventually some new devices. So what I'd like to do is briefly introduce to you the field of spintronics, what that means, and then I want to show you how we develop these materials that we could use to, for example, incorporate into a magnetic disk drive to read ever smaller magnetic bits. And what we were able to do was to increase, within a small number of years, the storage capacity of a disk drive by about 1,000-fold. And this is an enormous increase, and at least I like to think this is what makes possible today the modern information world, where all information is accessible, all of it is stored eventually on these magnetic disk drives. Now, beyond magnetic disk drives, we can also potentially have an impact on other types of storage and memory and logic devices. And I want to tell you about a type of memory, a solid-state memory, that we proposed actually in 1995. It still hasn't made its way into the marketplace in any significant way, but recent developments in materials and physics promises that we could develop a new type of solid-state memory that could be more capacious, cheaper, more reliable, and faster than any other known memory today. So it looks pretty good. And then finally, I want to discuss another technology that I proposed. I've called it Racetrack Memory. And this is also a solid-state memory based on advances in spintronics in just the past 2 or 3 years, which I believe will enable us eventually to replace magnetic disk drives, which are cumbersome mechanical objects dating back more than 50 years, with a solid-state memory device that would be as cheap as this magnetic disk drive, but would be about 1 million times faster and use much less power. And then finally, if there's time, I'd like to discuss some more recent work of our own, where we want to use currents not of spins and not of electrons, as we used in nearly all memory and logic devices today, but currents of ions, charged particles, charged atoms. And in some sense, this mimics how the brain operates. And eventually, we want to build new types of cognitive devices in hardware that could mimic certain components of the brain and potentially allow us to build new computing devices that could be more powerful than even those we know today. So this is what I'd like to cover in the next 45 minutes or so. And of course, you're welcome to ask questions if you have any questions. So first, let's put all this in perspective. And you've all heard of Moore's law, which describes how the computing power of silicon-based devices has evolved over the last 40 years. And essentially, there's a similar exponential increase in our ability to store digital data. And this is a very interesting paper. It's about 2 years old in Science, where they basically tried to take all different types of devices known to mankind that store information and store how the total storage capacity of the whole world has evolved over the last, in this case, 2 decades. And this is a logarithmic scale. So there has been a many orders of magnitude increase in the total capacity of all these storage devices all over the world. But more importantly, you can see that the color of the devices, these are all orange. These are analog devices, paper, film, videotape. And what's happened in just the past decade is essentially we've transformed all the way we store data from an analog form to a completely digital form. And this digital form has evolved extremely quickly in just, as I said, the past decade. And this is really what makes possible, for example, your ability to do a Google search. And essentially you're searching on all the information in the world at the same time. Only possible because it's digital and therefore accessible via the internet because we could store it on digital devices. And this, we like to think, and in fact is the case, this evolution in the past decade happened because of Spintronics. So that's what I'd like to discuss in this perspective. So we've had a huge impact in just the past 10 years. But the ability to store data using magnetism, of course, is a very old concept. Of course, biologically, we've done that for many millennia or longer. But in terms of real devices, then the earliest form was this thing called a magnetic core memory. Perhaps some of you might be familiar with that. It's a very simple, maybe some of you? Yeah, great. A very simple concept in which you take here, this is an annulus of a very soft magnetic material. And that magnetic material is magnetized in one of two directions. It's magnetized around the circumference of this annulus in a clockwise or in an anti-clockwise direction. And in fact, this is a very clever magnetic storage device because the information then is encoded as the direction of magnetization, a clockwise or an anti-clockwise direction. And chirality, it turns out, plays a very important role in magnetism. I want to allude to that a little bit later. And in this case, you can see how this technology worked. These objects, which were about several millimeters in size, through the middle of this annulus are passed wires. You can see some green and some pink wires. These are simply copper wires. And by passing currents along these wires, we can generate magnetic fields. And these are the fields that are used to change the direction of magnetization from one chirality to the other. Now, this type of magnetic core memory is apparently still used, for example, in some spacecraft, because it's very reliable and immune to radiation. But, of course, the problem with this technology is it does not scale. It requires the wiring of these wires passing through the center of this annulus, essentially a mechanical construct, which does not lend itself to scaling to smaller and smaller dimensions that would be needed to expand the capacity of this drive. Now, this is actually a photograph I took of a magnetic core memory made by IBM half a century ago, which is in one of IBM's museums on the East Coast. However, some of the concepts inside that magnetic memory are important for building storage devices using magnetism. And I want to now discuss how we've used Spintronics to enable us, as I mentioned, to rapidly and dramatically increase the storage capacity, in particular, of a magnetic disk drive. And so, as you all know, conventional electronics uses electrons, and it uses them in two particular ways. It uses the charge of the electron to store information in the forms of numbers of electrons stored in capacitors. This is, for example, you might be familiar with dynamic random access memory, the main memory of a computer. And also we can build devices by monitoring currents, flows of electrons, how many electrons are passing per unit time along a wire. Now, an electron has another property called spin, which I'm going to briefly discuss. And Spintronics is essentially the field, or the research field, in which we manipulate not currents of electron charges, but currents of electrons polarized, spin polarized in a particular direction. I'm going to come back to that in the next foil. And so essentially what Spintronics is about creating materials atom by atom or atomic layer by atomic layer, in which by, for example, applying a magnetic field, we can change the magnetic orientation of certain components in this agglomerate, and that changes the ability of electrons of particular spin polarization to pass through the material. I'm going to discuss that in a little bit of time. And this, essentially what I'd like to briefly discuss here, is something we invented, or I invented, called a spin valve, which is a very sensitive detector of magnetic fields. And then following that, I'm going to briefly discuss another type of device, a magnetic tunnel junction, and then I want to show you how new types of spintronic physics enables us to build solid-state memories of a conventional type and then of this magnetic racetrack type. And then finally, I want to talk about our ability to build a synaptic component in the brain using a magnetic tunnel junction in this way. And our goal here is eventually to build some brain in a box, we call it, some new type of computing device. That's what I'd like to discuss. So just back to basics, then, as I mentioned, an electron has a charge, and it has a spin. Now, spin is a little bit difficult concept to discuss, but it's often referred to that an electron, a charged object, has an angular momentum, just like a mechanical object can be rotated in a clockwise or in an anti-clockwise direction. An electron has a so-called spin, a spin angular momentum, and this quantity, which is quantum mechanical, is quantized. So it can only take two values. In the case of an electron, it's a spin half or minus half. Or we simply say, I'm going to say the electron has a spin up or a spin down. So it has only two flavors of spin. This is very, very important. And associated with that spin is the magnetic moment of the electron, which means that electrons passing through wires will generate magnetic fields. And we could use those in interesting ways. So this is all I'm going to say about the spin. But you have to recognize it's quantum mechanical, it's quantized. It really gives rise to the magnetic properties of materials. And when the spins of all the electrons are oriented parallel to one another, and as I said, when we pass a current of electrons through a wire, we can control the spin orientation of these electrons using spintronic phenomena. So let's just briefly discuss then how we could do that. So for example, if we take copper, which is used to wire your homes, this copper is entirely non-magnetic. So if we have a battery, we produce a current. The current will consist of electrons, and there will be an equal number of electrons with spin up and an equal number with spin down. So we cannot distinguish any spin characteristic of these electrons in a non-magnetic material such as copper. However, if we take a material which has magnetism, such as iron or steel, then in that case, depending upon the orientation of the magnetic moment of that material, then the electrons which we introduce from a battery, initially equal numbers of electrons with spin up and spin down, it turns out that these electrons will be scattered at different rates in a magnetic material, because electrons whose spin is oriented parallel to the local magnetic moment essentially are scattered much less often than electrons whose spin is the opposite direction to the local magnetic moment direction. So what does this mean? This means we introduce a current from a source of unpolarized electrons, and within a very short distance and a small number of scattering lengths of the order of approximately 100 atomic scale lengths, then the current will essentially be carried by electrons of one spin orientation, because the other electrons are strongly scattered and no longer contribute to the current. So perhaps that makes sense, hopefully. This is a very important concept. So, and if you like, I'm going to color code the electrons. Spin up, you see, spin down is blue and spin up is red. So this means in this blue material magnetized in the direction of these blue electrons, if you like, these blue electrons are much less strongly scattered, and so within a short number of scattering lengths, the current will largely be carried by these blue electrons. And this is shown here. Let's say it's 75% carried by electrons blue and only 25% carried by red. So the current is spin polarized. Now, why is this important? It's important because we can make structures on very short length scales. So in this cartoon, we have two magnetic layers and separated by a thin layer of copper, which is non-magnetic. And we do this on short length scales compared to these scattering lengths. Now what happens? Then if we introduce this current on the left-hand side, the current flows through all these layers, but in the blue layer, then the electrons will be polarized in the blue direction. This layer at the bottom, you see this white arrow, means the magnetic moment of this layer is magnetized to your right. But the red layer on top is the same material. It could be, for example, nickel, iron, or cobalt. These are typical magnetic materials. The layer on the top is colored red. Its magnetic moment is pointing to your left. And in this layer, the current, the electrons which carry the current are the red electrons, because those ones are least scattered. Now, what does that mean? Now, on the other hand, electrons actually are not traveling in straightforward to the rightmost direction, the direction in which we introduce the current. The electrons will be passing all over these layers. And so these blue electrons, which were least strongly scattered here, will cross this relatively thin copper layer and will be scattered in the top red layer. And the red electrons, which like this red layer, will eventually see this blue layer and be strongly scattered. So all the electrons, no matter where they are, will eventually be scattered. And the resistance of this structure will be high compared to the case in which we have the same sandwich of two magnetic layers. But in this case, the magnetic moments of these layers are aligned parallel to each other. So in this case, each of the magnetic layers prefers that the electrons are colored blue. So in this case, effectively, we have a short circuit through the sandwich of the blue electrons can travel very, very easily. So the resistance of this configuration will be lower than the resistance of the upper configuration. And essentially what this is, and what we called it a spin valve, because essentially we're turning on and off currents of spin-polarized electrons. So it's a very simple concept. If you have this sandwich of two magnetic layers, when their moments are antiparallel, because the electrons essentially see all these layers through this intermediate layer through which they can be transported, the resistance is high. And if we apply a magnetic field, so the moments want to be parallel to the field, just like two compass needles, they will want to be parallel to the magnetic field we apply. In that case, the resistance will be lowered. So essentially, this is a valve for spin-polarized electrons. Very simple concept, but it turns out this simple concept enables us to build a device that can sense the magnetic field much more sensitively than any other device. So we apply a magnetic field. The magnetic field, for example, would change this magnetic orientation of this red layer, so it's along the magnetic field, and we will lower the resistance of the structure.
I'm sorry, when you change that layer from red to blue,
Yeah.
So you're not changing the material, you're changing.
That's right.
You're changing an applied field.
Yeah, we're applying a magnetic field, and in this,
Applied like through
yeah,
a coil?
could be a coil. It's the most direct application. It could be a hard magnetic material, which will then magnetize the magnetic layer. But you're right, a magnetic coil or even a wire through which we pass a current, that will generate a magnetic field. So you're quite right. We're not changing the orientation of any atoms. Each atom in this particular case is a magnetic atom. So in that particular atom, the electrons want to have their spins within the atom oriented parallel to one another. This is called an exchange interaction. And so each atom has a magnetic moment, and each atom then is magnetized in the same direction through this exchange interaction. So the block of material is magnetized together. By applying a magnetic field, we can change the orientation of all these magnetic atoms together. We're not changing the atoms themselves, just the electron spins, so they will be reoriented parallel to the field. Does that make sense?
Sure, and you can do that quickly.
We can do it. It turns out, it's a very good question. Turns out with a coil, it's not so easy to do it quickly. It depends on the strength of the magnetic field. So for example, well, if you have an electromagnet, like motors, then they can generate magnetic fields, large ones, but very slowly. So to do it quickly, we need tiny, tiny coils. Then we can pass through currents on, say, the nanosecond timescale, maybe even the picosecond timescale. It's a very good question. It turns out to create very strong magnetic fields on very short timescales, the best approach is to go and to use a synchrotron and then use a powerful current of electrons or positrons. And the intensity is so great that will create very large magnetic fields on extremely short timescales, on, say, the femtosecond timescale. Wouldn't fit in the laptop. So you're quite right. What we want to do is develop materials and devices that are actually useful. Yeah, so hopefully that kind of makes sense. So this is a very simple, neat, very elegant concept that we can, by changing the magnetic configuration of magnetic components of inhomogeneous magnetic systems, we can change the way the current flows through them because of the innate idea that any current flowing through a magnetic material, inevitably the electrons will be polarized in the direction of magnetization. That's a very important concept that was developed in the 1930s. So this then is the idea, and this idea, this spin valve that we developed, arose from the discovery of something you might have heard of. It's called giant magnetoresistance, which is a property that was originally discovered by Peter Grunberg and Albert Fert, who then were awarded the Nobel Prize in 2007. And what they found was, at very low temperatures, they could change the resistance of a so-called magnetic multilayer. And this is my own work. I showed that we could see this phenomenon even at room temperature. In this system here, This is a magnetic multilayer. You see these blue and red layers represent magnetic material. This is mostly cobalt, separated by these ultra-thin layers of copper. And it turns out when this copper layer is sufficiently thin, it becomes slightly magnetic. And the magnetic layers, which are also atomically thin on either side of it, for particular thickness of copper, they will be oriented with their magnetic moments anti-parallel to one another. It turns out this is a very, very interesting phenomenon. And when you now apply a large magnetic field, about 40,000 times the Earth's magnetic field, these ultra-thin, atomically thin magnetic layers, separated by atomically thin copper, they can be reoriented so their moments are parallel, and the resistance of this multilayer drops. This is the resistance change in percent. So at zero field, this structure in which the alternating magnetic layers have their moments anti-parallel to one another, it's 2 times higher than the resistance in a large magnetic field, which is required to overcome the magnetic interaction through these ultra-thin copper layers. Now this type of structure, so Peter Grunberg and Albert Fert found this phenomenon at very low temperatures, well not super low temperatures, not in this system, but in magnetic layers of iron separated by magnetic layers of chromium. And then I showed essentially that this is a universal phenomenon, and we could create materials that showed large effects even at room temperature. And we then developed this thing we called the spin valve, whereby essentially spin engineering, we could create structures in which the magnetic moment of one layer is essentially fixed for all fields that we might apply by using a trick, by coupling a magnetic film to another type of magnetic material. It's called an antiferromagnet. There's no net magnetization, but at the interface there's an internal magnetic field that this layer sees. So essentially that moment is fixed by this spin engineering concept. We then have a layer of copper which is a lot thicker than in these multi-layers. So there's no net magnetic interaction between these layers. And then we have a second magnetic layer on the other side of the sandwich, which is the layer that will then change its moment in response to magnetic fields which are as small as the Earth's magnetic field or smaller. So we're extremely sensitive to detect tiny magnetic fields in this sandwich structure. And this is what we invented, and then were able to show we could use this in a very important application, which is that of a magnetic disk drive. So a magnetic disk drive essentially has today glass disks shown here, and each surface of this disk is covered with a magnetic film. And this magnetic film, a magnetic material, rather complex, is magnetized in tiny regions, shown here as these red and blue regions, around the circumference of this disk. And essentially, information then is stored as the boundary between one magnetic region and the next. It's these boundaries that store the information, a 0 or a 1. If we have a boundary, that's a 1. If there's no boundary, then it's a 0. Now, it turns out this technology of a magnetic disk drive is essentially a technology that has evolved using laws or rules of the technology that were written down more than 50 years ago. And IBM first introduced and invented this concept of a magnetic disk drive. So today, the device that is reading and writing this information, we call this the recording head. And this recording head is flown above the surface of this disk, which the disk is rotating, and the head is moved backwards and forwards radially, but it's flying today at 1 nanometer above the surface of the disk during operation. Essentially, 5 atomic spacings separates the recording head from the surface of this magnetic film. It's quite an amazing, remarkable technology. And essentially, the boundaries here between these magnetic bits develop tiny fringing magnetic fields, basically the flux coming from these magnetized regions, and we can detect that using this spin valve sensing device that is essentially deposited on the rear end of this recording head. It's a very tiny ceramic object that is flying above the surface of this magnetic film. So the secret of this technology is to make these magnetic regions as small as possible. Now, when you do that, the magnetic flux and the magnetic field you need to detect is going to get smaller and smaller and smaller. So before our spin valve technology, we were essentially at the limit, the end of the technology roadmap, if you like. But by introducing this new concept, this spintronic device, within 5 years, we could reduce the size of these magnetic regions by about 1,000-fold, and therefore increase the storage capacity 1,000-fold, which is quite remarkable. So that's what the first most important application of spintronics. And it turns out it was comparatively quick. We introduced or invented this spin valve sensor in 1990, 1991, and by 1997, IBM had introduced its first disk drive using this technology, which put IBM ahead of all the other competitors for several years before they could catch up. What does this mean? Then if we look at a disk drive from 1962, this device is about the size of a very, very big refrigerator, and it has 50 disks. Each of these disks is 24 inches in diameter, and the total storage capacity of this drive is 28 megabytes. It's very, very tiny, as you can imagine. But the technology, the concept of this drive, you see, this is, again, I've photographed this from a drive that was in one of IBM's factory here in San Jose. But the technology, you can see you have a disk, and here is the old head, the recording head. It's massive. But the basic concept is today the same. But today, instead of 28 megabytes in these 50 disks, in a single disk, we can store about 1 terabyte of data in a drive disk which is 2.5 inches in diameter. So that, it turns out, is 9 orders of improvement in capacity of disk drives in 50 years. It's quite remarkable. Unfortunately, we're coming now again to what is perceived to be the end of the technology roadmap for disk drives. We need something else. And I'm going to show you later on that I think it's possible with Spintronics to replace this technology with something I've called Racetrack Memory. So just to summarize then, so basically basic fundamental ideas of creating and manipulating currents of spin-polarized electrons have enabled us to create an incredibly sensitive detector of tiny magnetic fields. It's still the most sensitive detector of magnetic fields known at room temperature. And essentially, what this means today is that it makes possible miniaturization of hard disk drives and essentially access to all information in the world. Now I want to quickly then turn to a slightly different a device that actually has replaced the spin valve, but the essential spin engineering concepts that I invented actually are the same. And this is called a magnetic tunnel junction, and I want to show you how we could use this to build a solid-state memory device, not a disk drive. So this concept you can see in this cartoon. Again, it's similar. We have now, again, a sandwich of 2 magnetic layers. Here again, they're shown as color-coded red and blue, depending upon their magnetic orientation. But now, instead of having metallic layer separating these magnetic films, we have an insulating layer, a dielectric material, or even air. Now, the physics is totally different, and the current now is going to flow from one magnetic layer to the other across this insulating dielectric material. And now what happens is that the probability of electrons which are now quantum mechanically tunneling across essentially an insulator depends on the orientation of these magnetic films. Now it's been known, it was known for many years, since the 1970s, that if you extract current from the surface of a magnetic material, the current will inevitably be spin polarized, and you will extract more electrons of one spin orientation than the other. And this is fundamentally because of the magnetism of this material, and the electronic structure now breaks symmetry, and there will be more electrons of one spin orientation than the other spin orientation at the so-called Fermi energy from where the electrons will tunnel. And now it turns out then, if we have these magnetic layers being parallel, then electrons can readily tunnel from states which are spin polarized in one direction to empty states of the same spin orientation. During this tunneling process, the spin of the electron will be conserved. It's a very short process. But if we reverse the direction of one of these magnetic layers, now the tunneling probability is reduced because there are smaller numbers of states of the same spin polarization into which the electrons can tunnel. So essentially now, by really changing again the relative orientation of these layers from parallel to antiparallel, we can change the tunneling current. But unlike the metallic spin valves, where we had the copper separating these magnetic layers, the results are much bigger. And instead of changing the resistance, as I showed you in a multi-layered structure, by a factor of 2, or in a spin valve, the change in resistance is only 10%. That's all that is needed to make this extremely sensitive detector of magnetic fields. Now the change in the tunneling current can be up to a factor of 10 at room temperature. It's much bigger. It's not a vacuum, it's going to be an insulating material. Typically, it would be, for example, aluminum oxide. And I'm going to show you, using magnesium oxide, we can improve things. It could be vacuum, though. That's certainly possible. Essentially, it's just a material in which there are no electronic states. So, but more importantly, it turns out that since essentially there's nothing here, if you like, then the tunneling probability decreases exponentially as we increase the thickness of this spacer dielectric material. So it means we can tune the resistance of this structure by many orders of magnitude without changing this so-called tunneling magnetoresistance, the change in the resistance when we change the orientation of these magnetic layers. So from technological perspective, it has some unique properties. Now, to answer your question briefly, I mentioned we have to control the magnetic moment directions in these sandwiches using what I'm going to call spin engineering concepts. And essentially, we need to change, this is a diagram of how the magnetic moment responds to a magnetic field. And essentially, usually, magnetic materials, this response curve, or hysteresis curve, will be symmetrical, about zero magnetic field. But we can change this by coupling this magnetic material to what is called an antiferromagnet. It's a material which locally the magnetic moments of atoms want to be antiparallel to each other from one atomic site to the next. So in essence, there's no net magnetization, except at an interface, this is broken, and it turns out there is a small net imbalance in the moments of this antiferromagnetic material, leading to a very, very strong internal magnetic field that can be enormous. And this can be used to set the direction of the magnetization of one of these layers. So the hysteresis loop is now no longer centered at zero field. It's centered at what is often called this exchange bias field. But what it really means is, for all useful fields we will apply, this magnetic moment of one of these layers is essentially insensitive to field, and only the other magnetic moment responds. So if you like, as a function of magnetic field, the resistance shows this beautiful hysteresis curve. At higher magnetic fields, these are relatively small fields. This is about 100 times the Earth's magnetic field. The moments are parallel. The tunneling current is much higher. Resistance is low. And when we change the orientation of one magnetic layer, the resistance is increased. And using, this is your question, it turns out that the best insulating material that has been known for some time was this material here. We're using here a beam of electrons transmitted through a tiny sliver of this material that we've created. And you can see then we have to use electrons, which have very short wavelengths, so we can see the individual atoms in these structures. And what you can see, this is the magnetic material. You can see atomic layers in the structure. But in the insulating dielectric material, which separates the upper and lower magnetic layers, you can see there's no structure. This is so-called an amorphous material, and it's formed from an aluminum oxide material. And since it's amorphous, the electrons that tunnel essentially really pay no attention to this material. This material is used because it turns out that to create useful tunnel junction devices where we can measure some current, this barrier, this insulating layer, has to be very thin, a few atomic layers thick. Otherwise, there's no current. The probability of tunneling across the layer is too small. And aluminum oxide was a material that was discovered in the 1980s, could lead to ability to make devices for superconducting Josephson junction-based computing devices that IBM and Hitachi were developing. And so this is the insulating material that we initially used for these tunnel junction devices, for the magnetic tunnel junction devices. Now it turns out that there's a better oxide material that we first showed in 2001 could replace what till then was the best known material, this aluminum oxide. And this is a very simple oxide. It's called magnesium oxide, a simple cubic material. And can you see in this, again, this is an electron, transmission electron micrograph through the multilayer. You can see in this case, the insulating material also, you can see these atomic layers. Now it's crystalline. And it turns out because it's crystalline, the wave function symmetry of the electrons that are tunneling is important. And it turns out if we use special magnetic materials, in particular cobalt iron alloy, which has a certain type of crystal structure, then it turns out that the electrons of this spin orientation, this blue spin orientation, their wave function is very delocalized. So the probability of tunneling is much higher across this insulating material than the red electrons, which are much more localized. So their wave function barely makes it at all across this insulating material. And so essentially, it's an amazing result. This crystalline, non-magnetic material essentially filters out, or spin filters, the electrical current, so that instead of having a current that might have been 50% spin polarized, it can be nearly 100% spin polarized. So this was a remarkable theoretical prediction which we first showed experimentally. And what does it mean? It means that if we look at the magnitude of what I've called this tunneling magnetoresistance, the percentage change in resistance of this tunneling junction when you change the magnetic layers from being parallel to antiparallel, in 1991 was the first observation of any tunneling magnetoresistance at room temperature. And 2001 was when we found this magnesium oxide material. You can see today, we can see changes in resistance of nearly 800% at room temperature. So there's been a remarkable discovery of materials and this physical phenomenon in just the last 15 years or so. And so what does that mean? It means, it turns out, since this discovery, we made it in 2001 and we patented it shortly afterwards, it means that since 2007, magnetic disk drives, the information is detected not using this metallic spin valve, but using this magnetic tunneling junction device. Although, if you looked at the device, it would look very similar from a structural perspective and a spin engineering perspective. So now, that was the story about magnetic tunneling. Now, how do we make these materials, which, as I've said, I've emphasized several times, involve layers of different materials deposited one on top of each other, atomic layer by atomic layer? It turns out there are a variety of techniques, but this is a system that we built in my laboratory at IBM in San Jose. It's taken about 10 years, and it's cost about $10 million, and the size is about 40 feet by 40 feet. And can you see there's a central robotics chamber which is connected to a series of ultra-high vacuum chambers. And we can use different techniques for depositing these atomically thin layers. So we use techniques such as molecular beam epitaxy, something called PLD, pulsed laser deposition, and something called magnetron and ion beam sputtering. And in this system, we actually have about 80 different sources of materials. So we have an ability to explore a wide range of materials. That's all I want to say about this. What's remarkable, though, is we can actually, in the laboratory, see materials whose properties depend on these atomically thin layers. And we can actually take these and manufacture them on a mass scale. So let me just come briefly now to how do we replace a magnetic disk drive. Now, conventionally, a solid-state memory is essentially built like this. It consists of a so-called cross-point array. Essentially, you have a series of parallel metal lines. These are shown here. And you have a set of orthogonal parallel lines above. And essentially, between each of these lines, we insert a resistive device. We can insert this tunnel junction device because we can tune its resistance so that it gives just the resistance we need to detect its state by passing tiny currents. So if we pass a current along this word line and then exit the current through a particular bit line, we can detect the resistance of this magnetic tunnel junction state. And if the magnetic layers are parallel, we're going to detect a big current. If they're antiparallel, we're going to detect a small current. And in this way, we can read whether the state is a 0 or a 1. So we design the tunnel junction now to be essentially have only two states. Now, we proposed this then in, as I said, in 1995, and built the first device in 1999. And in that time, we read the device very trivially by passing currents. We can do that on the nanosecond time scale. But to write it, we passed currents along these same wires. So by passing a current along a word line, this would generate this circumferential field. This is just through Ampere's law. And so this means all these resistive devices along one line see the same magnetic field. So to write a particular device, simultaneously you pass a current along a bit line. And so this particular device will see the magnetic field from this current plus the magnetic field from this current. And then by design, we design it so the combination of those two fields will change the magnetic state. So the magnetic layer in the sandwich or the tunnel junction will be rotated from being parallel to being antiparallel to that reference layer, which is immune to these magnetic fields. And so if we want to write in a different orientation, we simply reverse the direction of the current through these bit lines. So we can actually write multiple devices all at the same time. Now it turns out this concept of using magnetic fields to write is a very bad concept, and it doesn't scale. So that as you shrink the current line diameter, the magnetic field gets smaller for the same current. So you need to use much bigger currents. This doesn't work fundamentally, although it's possible to build a device. So let me just summarize briefly. What I've shown you is this magnetic tunnel junction sensing device is a beautiful spintronic device which gives rise to huge changes in its resistance when in the presence of magnetic fields, and we could use that then to detect ever smaller magnetic bits in a disk drive. And this is the technology that's been used for about the last 5 or 6 years in magnetic disk drives. Now, as I alluded to, the disk drive is, the reason why we use it is because today it's extremely cheap because of our spintronic devices. However, at the same time, it's obviously slow, because a mechanical disk can only be rotated at a certain speed. So the access time is on the millisecond time scale. And it's also unreliable because I mentioned to you the recording device that is reading and writing is today only a few atomic layer spacings from the magnetic material. So perhaps some of you might have had what we call a disk drive crash, where the head bumps into the disk and you'll lose all the data in the drive. Now, you'll be surprised to know that happens actually quite often. So for companies which have large numbers of these disk drives to store a lot of data, this happens very frequently on a daily basis, and the disk drives have to be replaced. So this is not good. On the other hand, as I've said, we can build a variety of memory devices. This is a non-volatile solid-state memory using the same tunnel junction as a memory device. And in this way, we can build, for example, this 16 megabit Amram device that we built at IBM a few years ago. So it's certainly possible to do this. And this type of memory gives very high performance, nanosecond times to read and write, very good endurance. There's no obvious means by which the data is eroded. At the same time, though, the cost is very high. The cost of this memory device per bit is 100 times higher than a bit stored in a disk drive. So it's a 100-to-1 ratio. And this basically has been unchanged for the last several decades. It's not going to change in the near future. Both of these technologies, quite frankly, have problems in scaling beyond the next few generations. The physics doesn't allow for that. We need to do something very different. What we'd like to do is have a device that would be as cheap as a disk drive per bit, but would be as fast as this type of memory, which would be wonderful. And one way to do that, I've proposed, is something I've called this magnetic racetrack memory. And the concept is very different from any other proposed memory. And what is the concept? The concept now is that we build a magnetic nanowire vertically above the surface of a silicon wafer. We use conventional silicon microelectronics to provide reading and writing and detection devices, But each of these racetracks is comprised, you see, of magnetic regions, red and blue, perhaps 100, and using a very interesting new concept in Spintronics, by simply passing a current through this wire, all of these magnetic bits can be moved around the wire. So we're not moving any atoms. We're simply changing the direction of the local magnetization from one direction to another so that all these magnetic regions move around the racetrack. That's a pretty neat concept. So what does that mean? That means in a silicon wafer, where originally you had one bit of information stored in this cross-point array, we can now store 100 bits in the same area of silicon. Therefore, we can reduce the cost by 100-fold. So this racetrack memory promises a solid-state device that would be as cheap as a disk drive, but would be as powerful in terms of reading and writing as this conventional solid-state memories without any wear out at all. So this looks extremely attractive. This is something I proposed just a few years ago, and we've demonstrated in the last few years. And so let me try to discuss a little bit of the physics underlying this concept. And the most important physics, which was proposed by John Solzhenitsyn and Luc Berger quite a few years ago, is this simple concept. Firstly, it relates to this concept I discussed just at the very beginning. You pass a current from a battery, unpolarized. Because of scattering, which is spin-dependent, quickly the current becomes a current of electrons whose spins are parallel to one another. And spin means electrons have what is called spin angular momentum. Just like a mechanical object has angular momentum, spin have this quantum mechanical equivalent spin angular momentum, which is also conserved. So now let's take this. This is a cartoon of a homogeneous magnetic nanowire. And on the left-hand side, you see the magnetic moments on the atoms have their moments all parallel to each other, pointing to your right. And on here, on the right-hand side, the local magnetic moments on each atom are pointing to your left. And in between, we have a boundary. This is called a domain wall. And this wall separating these regions of magnetization on the nanoscale has extremely interesting properties. And these domain walls themselves are really topological objects which behave like an object of mass. It has momentum. More importantly, though, now if we pass a current through this wire, the current, you see these electrons, their spins will be parallel to this local magnetic moment direction. And when this electron crosses this domain wall, you'll see adiabatically its spin will rotate to be parallel to the magnetization of the opposite magnetic region. And so as the electron spin rotates, it delivers a quantum of spin angular momentum to this magnetic system. And in response, a local magnetic moment rotates. And what happens is for each electron that is spin polarized, that passes the domain wall, a single magnetic atom will rotate its moment direction to preserve in totality the angular momentum of the system. So if we pass enough electrons, enough of these moments will be rotated that the domain wall will move. So does that make sense? Very simple concept. We're not moving any atoms, we're not doing anything except passing a current. In response, the magnetic moments rotate and effectively the domain wall will move. That's what happens. So the physics by which we transfer the angular momentum, the spin angular momentum from the spin-polarized electrical current to this magnetic system is extremely interesting and has been developed just in the past 5 or 6 years. So this is one mechanism by which we could use currents of spin-polarized electrons to manipulate magnetization. This is a very interesting area of research today. So now why is it interesting for this racetrack? So let me show you that by simulation. Here, for example, is a homogeneous magnetic wire. And the colors represent the direction of the local magnetic moments. So red, you can see, is pointing to your right, and green to your left, and blue is pointing up, and yellow will be down. And now the basic concept is this. If we have a uniform magnetic wire, and here is this domain wall I mentioned. These are two regions where the magnetic moments are pointing north pole to north pole. Inevitably, the next domain wall, you see these two regions have their north poles pointing away from each other. Now, until just a few years ago, the only way of manipulating the magnetic moments in this wire was to apply a magnetic field. If you apply a magnetic field, like all compass needles, the North Pole will rotate towards the field. Same thing happens here. We can simulate that using just solving some equations. And what you see then is the two domain walls will move together because the magnetic field favors this red direction. So the red becomes, does that make sense? So we go back. So we just go back. And you see the red regions will grow because the magnetic field will favor all the compass needles to point in the red direction. Now that means we can't build racetrack memory. Now on the other hand, if we now do something very different, we simply pass a current through this wire. Now in this red region, the current will be carried by red spin-polarized electrons, and in the green region by green. And when these electrons cross the wall, this domain the two domain walls will move in the same direction. So let's show you that. So this is what happens. We pass current in this direction, the electrons are flowing in this direction, and the domain walls move in the direction of flow of spin angular momentum. Does that make sense? So this is an amazing proposal made just a few years ago, and we were actually the first to demonstrate we could move a series of domain walls in this way. And so this is the most amazing point. We can shift a series of domain walls together just by passing a current from a battery. No more than that. And this is a very exciting development, and this essentially is what was needed for racetrack. So I proposed this, and then we demonstrated the physics. It was possible. And if we can build this essentially three-dimensional version where the nanowires are pointing in the third dimension, we can build a device which would have the storage capacity of a magnetic disk drive, a storage capacity 100 times greater than any memory device today. And on the other hand, if we do something simpler technologically, we build these racetracks horizontally above a silicon wafer, then we could build a memory device which would have the storage capacity of flash. So all of you use USB memory sticks. These are built using flash, which is the cheapest memory technology today. But the cheapest memory technology today means in flash, which is a capacitive memory, you can write it only 100 times before you destroy the memory. So that is a severe limitation of flash memory, although I must admit my computer here uses flash memory because it's much faster than a magnetic disk drive. But it has this little bit of a problem that if you write it too many times, you'll just lose all the information. Now, that's the problem. So this means, of course, with our racetrack memory, we never lose information. We can write it indefinitely. So compared to flash, we estimate we would have the same cost, but we would use 50 times less energy, and it would be about 1 million times faster. So it would be, again, create new types of computing devices that were more energy efficient and more compact and more reliable and faster. So this is the basic idea. Unlike any other memory device, we store the memory in wires, the information, and we move the information to a single point along the racetrack for reading and a single point along the racetrack for writing. So we build a writing and a reading element per racetrack, and we simply move the information when we want to read or write it using current pulses. Now we've actually built a prototype of this memory just a couple of years ago. It's not a very good prototype, but it's proof of principle. It has 1,000 bits. These are 32 horizontal racetracks, and essentially it largely works. We can read, write, and move domain walls, which is the central memory element. Okay, this is a good question. You ask very good questions. The material here we're using is a soft magnetic material. It's made of nickel and iron. This is what these racetracks are made from. And these little devices here, these are tunnel junction devices we've incorporated into the racetrack for the purposes of reading the domains that we're moving to and fro. So to a couple of some points here. Firstly, racetrack memory wasn't possible even 5 years ago. So it's just new discoveries in Spintronics have enabled this, I think, very interesting new memory. And it's essentially new materials, which are the key, atomically engineered materials. And also wanted to point out, this is innately three-dimensional. And all of silicon today is innately two-dimensional. And we can't essentially squash any more transistors into a two-dimensional array. Just like cities have to grow three-dimensionally, then silicon and magnetic disk drives both are innately two-dimensional. And you really need to think of devices which are more three-dimensional in nature, otherwise scaling is limited. Now, I did want to briefly then, you asked about materials. Currently we're using a class of magnetic materials which are very so-called soft, easily magnetized. And if we look, again, we simulate the properties of the domain walls in these materials. They have particular characteristics. It turns out they're chiral. They have clockwise and anti-clockwise so-called vortex and transverse walls. I don't have time to discuss this, but it turns out that we can build interesting devices by controlling the chirality, and in networks of magnetic wires, the chirality of the domain walls will determine how they flow through the network. So we think this is pretty interesting for creating new types of logic devices. All I wanted to comment on here was that to build dense racetrack, we have to use materials where the racetrack wires have their magnetic moments oriented perpendicular to the racetrack. And we can do this again by using atomically layered materials in which, on the atomic scale, it turns out that the interfaces, for example, between atomically thin cobalt, these are about 1 atomic layer thick, and 3 atomic layers of nickel, then the magnetic moments want to be perpendicular. And what does that mean? This means that the domain walls can be much narrower. They can be atomically narrow in this configuration as compared to these soft materials. And it turns out that in the last couple of years, we've and others have discovered that these, I think I'm going to skip this, but it turns out that so let's compare briefly. We have these soft magnetic materials, large domain walls. We have these perpendicular magnetized materials in which the domain walls are much, much narrower. And now if we look just briefly at the velocity of domain walls as a function of the density of current, then in conventional materials like this, then the domain walls move along the electron flow, as I mentioned, along the direction of the flow of spin angular momentum at velocities of the order of 50 meters per second for reasonable current densities. Now, what was discovered just 3 years ago was that in materials, which I just showed you, ultra-thin, perpendicularly magnetized materials, which are grown on heavy metals like platinum, then the domain walls move much faster, 5 or 6 times faster for the same current density, and they move in the wrong direction. They move in the direction of current flow. And it turns out this is because of an entirely new interaction of current and magnetization, and it's because in these heavy metal layers, a charge current generates a pure spin current, which can interact with the domain walls and move them more efficiently in the opposite direction. Well, this is a very exciting development, and what we've done is we've used these materials to build a racetrack. Here you can see 20 domain walls. This layer is only 6 atomic layers thick. We can image using a special type of microscope, and you see these walls are being moved backwards and forwards with nanosecond long current pulses. So this is essentially the way to build racetrack memory. Now, finally, point is that the domain walls here are chiral. Very exciting development. No time to discuss. But if there's any time, maybe we're running out of time, then if in the last maybe 2 minutes, I just wanted to, we've talked about storage and how we could use spin currents to generate new sensing devices. We've already created the ability to store all information. We're building new types of non-volatile magnetic memories. We've got racetrack memory. And this is just 1 second. I wanted to say that beyond storage, the other major components of computers are the computing devices. And I just wanted to comment that conventional silicon-based computers are entirely different from the brain in particular. So we want to find inspiration from the brain to devise new types of means of computing. And in particular, this type of silicon computer uses enormous amounts of power when it's essentially doing nothing. More than half the power in today's computers is just wasted. Whereas the brain is much more efficient, and essentially when it's doing nothing, it uses much less power. And of course, as you all know, we are capable, some of us, some of you, of learning, reconfiguring yourselves to develop new abilities to compute. And the brain is certainly much better at certain types of operations than conventional silicon-based computers. The point I wanted to make was that if we look at the brain, it's a very, very interesting construct where computing devices, the neurons, are connected through wires that evolve, that reconfigure themselves as we utilize the brain. And each neuron is connected to about 20,000 of these synaptic connections. And the point is that if we look at the brains of various mammals, mouse, rat, human, and we compare, let's say, the computing performance of the rat, we see that its computational power is about 78 teraflops, is about the same as this very powerful so-called blue gene computer from IBM, about 3 years old, which has 32,000 processors. And a brain has about the same amount of memory estimated, 7 terabytes compared to 8 terabytes. But what is most important is that if we look at the energy consumed by this rat, it consumes 1 million times less energy than this blue gene computer, 50 milliwatts compared to 400 kilowatts, and of course it's much smaller. So somehow or other, biologically, it's 1 million times more efficient than today's silicon-based computers. So at least we have a goal, and many others, of building a new type of electronics, we don't know how to do it, which we would call neuromorphic, in which essentially it's much more connected, just like the brain, and which is much more efficient for reasons that we haven't fully understood. And I think I'm running out of time, so I'm going to skip this, but the brain operates in certain ways which we can emulate in Spintronics. I'm going to skip this then, and I'm going to skip this. And maybe my final conclusion will be that Spintronics is a very exciting area of research because not only we're discovering all sorts of new physics, in particular involving the spin of the electron and how to manipulate currents of electron spins in various ways in atomically engineered materials, but we've used this already to change the world in terms of building disk drives that are 1,000 times or more capacious. And I proposed, for example, this Racetrack Memory, which is truly three-dimensional. My final point is we really need to move away from existing technologies to new technologies, taking advantage of this new physics and moving into the third dimension. And this is my own mind why I think trying to mimic how the brain is constructed, how it operates, is also very exciting, and that also is truly three-dimensional. So I think, and then the final point would be that we're coming at the end of one of these technology epochs. If you look over the last 100 years, then this is a very interesting plot of what $1,000 will buy you in terms of computational performance. And this, of course, has increased, you see, this is 17 orders of magnitude over a century. And we've gone through various eras of computing, mechanical, electromechanical, vacuum tube, discrete transistor. Today we're in this integrated circuit. It's lasted 40 years, but we've come to the end. We cannot scale anymore in 2 dimensions. We need to do something else. It's not clear what it is. But in my mind, spin currents. And if I'd had time, I would have told you about some of our more recent work on using currents of ions to mimic certain types of brain functionality. I think it's going to create very, very exciting science and technology in the coming years. So I'd like to thank you very much for your attention.
Questions? Only you, huh?
Got lots of questions. Anyway, wonderful talk. Thank you. You said that going to 3D is free. How do you fabricate that?
I didn't say it was free. I said it's certainly necessary. Well, there are many ways of fabricating three-dimensional structures. One is a technique, for example, called atomic layer deposition, where you can cover surfaces, vertical surfaces on the atomic scale using chemistry. By essentially introducing a certain type of chemical, it will bond to a surface and only will form one set of bonds. And then by chemical means, by changing the chemistry, you can essentially deposit atomic layers of many, many different types of materials, one after the other, on surfaces that are vertical. And so this is a very exciting technology. Of course, people know how to do that. It's already being used. For example, dynamic random access memory, the way IBM builds it, is a capacitor with a trench. Today, that trench is 100 times deeper than it is wide, and you need to cover the surfaces with particular types of metals and insulators to create the capacitor.
John? As a business matter, could you estimate how many scientists and engineers
are at your disposal or on your team to help achieve these goals?
Okay, that's a very interesting question because, for example, Racetrack Memory, that involves just 2 or 3 scientists, very tiny team, whereas the Amram, the magnetic random access memory, today there are hundreds of scientists. So we ourselves at IBM, we have a collaboration with Samsung, and Samsung has 150 scientists working on this. We also collaborate with Micron. So there's huge investments, hundreds and hundreds of millions of dollars today invested in building this magnetic random access memory using magnetic tunnel junction storage elements. Racetrack, which is going to take a few more years, then there's very little investment indeed. But it's much more exciting in my mind.
I remember like 15, 20 years ago, they had bubble memory was going to be a big thing. I was wondering if this evolved from that, just out of curiosity.
Bubble memory is very interesting. In fact, bubble memory is kind of coming back, not in this way. It turns out that magnetic bubbles had the problem that in those days one didn't know about spintronics and manipulating magnetization with spin currents. So the only way of moving magnetic bubbles around was with magnetic fields. And as I pointed out, very tough. But today there's a lot of interest in Racetrack, a little bit something related to a bubble. Now it's called a skyrmion. And a skyrmion is a topologically protected object. It looks like a region of magnetization that is reversed in a otherwise uniformly magnetized material. And certain materials which have very poor low symmetry will of themselves form arrays of these skyrmions. Each skyrmion looks like a magnetic bubble. And it turns out there's very, very interesting work initially by Christian Fleider at the Technical University of Munich, who showed that if you pass current through this array of skyrmions or bubbles, the whole array will rotate in the presence of currents and can be moved very low current densities. So some have argued that this could be an interesting approach to building something akin to Racetrack. But it turns out they move at very low currents. They also move very, very slowly, because fundamentally you still need spin angular momentum to manipulate these objects.
I have what is probably an embarrassingly simple question. I thought you were going to talk about memory in which you had electrons in one state and you flipped the spin. And you didn't, as I understood, you didn't talk about that at all.
Yeah.
So if you have just a bunch of electrons, you have a plasma full of electrons.
Right.
And some of them spin up and some of them spin down, just at random. Do those ever change, or is this
sure, they will change.
Just at random? Yeah,
at random. So typically, of course, you typically at any modest temperature there will be thermal fluctuations, thermal energies from the thermal bath, and that's sufficient to cause electrons, individual electrons, to flip their spins. So of tremendous interest today is using a single spin, for example, to imagine building quantum computers. And then what you're really alluding to is how long will an electron, a single electron spin, preserve its spin orientation. And this is on the scale of nanoseconds, hundreds of nanoseconds, maybe a microsecond, this sort of time scale.
Thank you for making my question seem intelligent.
Final question.
Oh, very good question.
Hi, I had a question about your molecular beam epitaxially deposited magnesium oxide. Does that go down naturally as a crystalline, or do you have to do something special? And does aluminum oxide ever go down crystalline?
That's a good question. So magnesium oxide actually wants to be crystalline, and it will always form this. It's a very, very simple oxide. It doesn't form any defects. It's always perfect oxide, which is why we use it, and it's a simple cubic material. Turns out what was critical, which is why we were first to show these giant tunneling resistance effects, is that if you have a magnetic material like cobalt iron and you try to deposit magnesium oxide, typically there'll be some oxygen in the system, and that oxygen will oxidize the magnetic metal, and then you no longer can form this. You need a perfect interface between the unoxidized magnetic material and magnesium oxide. Otherwise, typical magnetic materials like cobalt iron, when you form oxides, they actually form very strange magnetic structures, and you lose all the effects. So what we actually demonstrated, or I proposed, we actually form a thin layer of magnesium metal. Then we just 2 atomic layers thick, and then you introduce oxygen. It oxidizes, forms magnesium oxide, and you get a perfect interface. So the secret of making these tunnel junctions is forming perfectly crystalline, coherent interfaces between the magnetic metal, which is not oxidized at all, and the magnesium oxide. And it turns out it's possible in that particular case. Aluminum oxide can be crystalline. It turns out it is like sapphire. You can make it crystalline, but it typically requires very high temperatures. Otherwise, it's amorphous. Or if you grow it epitaxially on certain types of oxides, for example, you can grow it on, turns out on magnetite. It will form crystalline aluminum oxide over short distances.
All right, let's thank Stuart one final time. We just remind everybody we have refreshments in the courtyard in the coffee room.